Hello everyone, welcome to Physics online classes for class 12 students. Let us continue chapter 6 Electromagnetic Induction. Today we are going to derive an expression for self-inductance of solenoid. As we have studied in the previous class what is self-induction, and also we studied what is the coefficient of self-induction, or we can also call it as self-inductance. Yes, we know that self-induction is the phenomenon of induction of EMF, and hence current in the coil is due to variation of current in the same coil. So we already studied when the current changes in the coil, induced EMF takes place by itself, so we can call it as a self-induction. Then self-inductance is denoted by L, and it is defined as the EMF induced in the coil due to unit rate of change of current in the same coil. That is L equal to E divided by di by dt, and its SI unit is Henry. Then what is 1 Henry? 1 Henry is the self-inductance is said to be 1 Henry if 1 volt of EMF is induced in the coil when current is changed at the unit rate of 1 ampere per second in the same coil. Then we can say that 1 Henry. Now let us study self-inductance of solenoid. Let us derive an expression for self-inductance of a solenoid, or which is also called as coefficient of self-induction. Yes, here first we have to know what is a solenoid. Solenoid is a long coil of wire wrapped in many turns. So the main purpose of this solenoid is used to generate a controlled magnetic field through the coil. That's why we are using a solenoid here. This is a helical coil with n number of turns. Let us derive an expression for self-inductance of a solenoid. Before going to derive an expression for self-inductance of a solenoid, first we have to know what is a flux linkage. Yes, flux linkage is the product of number of turns of the coil and magnetic flux linked with the coil. What is flux linkage? It is the product of number of turns of the coil and magnetic flux linked with the coil. Generally, flux linkage is equal to N into pi. N is number of turns of the coil, pi is magnetic flux linked with the coil. So flux linkage is equal to what? N pi, and this gives the product of number of turns of the coil and magnetic flux linked with the coil. Right? Now you can observe this diagram. We considered a helical coil. Let us take small l, capital L and N. These three terms observe here. Small l is length of the given solenoid. Here this is a small l. Capital L is self-inductance of the solenoid, and capital N is number of turns of the solenoid. Let us consider small l, capital L and capital N. These are length, inductance, number of turns respectively of the solenoid. Now let us consider I amount of current is flowing through this solenoid, and small n gives number of turns per unit length of the solenoid. What is capital N? Number of turns. Total number of turns is capital N. Right? Number of turns per unit length. For 1 meter wire, how many turns are there? That is given by small n. Don't get confused with capital N and small n. Capital L and small l. Small l is the length of the solenoid. Capital L is self-inductance of the solenoid. Capital L, N is total number of turns in the solenoid. Small n is number of turns per unit length. You can observe these points. Let small l gives length of the solenoid. Capital A gives cross-sectional area of the solenoid. Small n, that is number of turns per unit length. Then capital N is N into L, cross multiply here, capital N equal to N into L. That gives a total number of turns in the solenoid. And L is self-inductance of the solenoid. I is current is flowing through the solenoid. Capital B is magnetic field produced inside the solenoid. Mu naught is absolute permeability of free space. Mu r is relative permeability. These points you have to remember before going to derive an expression. So we know that the flux linkage is directly proportional to the current in the solenoid. Observe here, I am going to write. So it shows that flux linkage is directly proportional to current in the solenoid. What it mean? What is a flux linkage? Flux linkage is given by N pi. N pi means what? The product of number of turns linked with the magnetic flux N pi. So this is directly proportional to current. Why? Because we know that when this magnetic flux linked with this number of turns of the coil changes, then induced EMF takes place, current is produced. If magnetic flux does not changes, then there is no current in the coil. That's why flux linkage is directly proportional to current in the solenoid. Therefore, I am going to write that is N pi is directly proportional to I. Flux linkage is directly proportional to current in the solenoid because when a magnetic flux linked with n number of turns changes, then current is produced. That's why N pi is directly proportional to I, or we can write N pi is equal to, I am going to write proportionality constant L into I. Or we can write here, we want self-inductance, so we can write L equal to N pi divided by I. Let us take it as equation number 1. What is L? L is self-inductance of the solenoid. N pi is flux linkage. I is current in the solenoid. Let us take it as equation number 1. Now, the second point. Magnetic flux linked with the solenoid is given by, we already studied about magnetic flux. Here I am going to write magnetic flux linked with the solenoid is given by. Magnetic flux linked with the solenoid is given by the equation. Magnetic flux is denoted by pi equal to B dot A, or we can write here pi equal to B dot A. B is magnetic field. In place of magnetic field, we know the equation we already studied in the previous chapter. You can remember moving charges and magnetism. There you have derived B equal to mu naught Ni. Right, mu naught is absolute permeability. N is number of turns per unit length. I is the current. Substitute here. In place of B, I am going to write mu naught Nia. Right. Pi equal to mu naught Nia, or we can write this equation as pi equal to mu naught, keep as it is. In place of N, I am going to write this equation. Observe here, capital N is equal to number of turns per unit length, right? Or we know that capital N equal to total number of turns. Total number of turns is N into L. So, but we want small n value. Small n means capital N divided by L. So, in place of small n, I am going to write capital N divided by L. Remaining is I into A. Now, let us take it as equation number 2. The first equation is all about self-inductance, and the second equation is magnetic flux linked with the solenoid. Now, from these two equations, let us substitute equation 2 in equation number 1. Substitute equation 2 in equation 1. So, equation 2 is pi equal to mu naught Nia divided by L. Equation 1 is L equal to N pi divided by I. So, here I am going to write L equal to N divided by I. Keep as it is. In place of pi, I am going to write mu naught N I A divided by L. Now solve this equation. L equal to, I can write here, mu naught N into N is N square. Mu naught N square, I will get to cancel. Remaining is A divided by L. Mu naught N square A divided by L. So this is an expression for self-inductance of a solenoid for free space. This is for free space because mu naught indicates absolute permeability. Suppose if the solenoid has a relative core of permeability. If solenoid has a relative core of permeability, then the equation can be written as L equal to mu naught mu R N square A divided by L. This is for relative permeability. Is it clear? What is the expression for self-inductance of a solenoid for free space? L equal to mu naught N square A by L. For relative permeability, we can write the equation as L equal to mu naught mu R N square A divided by L. So this is an expression for self-inductance of a solenoid, and this derivation carries 3 marks in your board examination. Now, the factors affecting self-inductance of the solenoid. What are the factors affecting self-inductance? Observe the final equation, mu naught N square A divided by L. These are the 4 terms that affects self-inductance. Observe here, the first point is length of the solenoid. See here, self-inductance of a solenoid. Here, induced EMF takes place when the variation of current is in the same coil. So that depends on the length. And the second point is number of turns. Number of turns in the solenoid, that is N. And the third one is cross-sectional area of the solenoid and relative permeability. So these are the 4 factors that affects the self-inductance of the solenoid. Or simply you can remember the equation L equal to mu naught N square A by L. Those 4 terms are itself affecting self-inductance of the solenoid. Then last note you can observe, self-inductance of a straight solenoid is almost negligible or it is equal to 0. When we considered straight conductor, number of turn will become 0. For the straight conductor, there is no number of turns. So N equal to 0. So we have the equation mu naught N square A divided by L. When N equal to 0, then L equal to 0. So self-inductance of a straight solenoid is almost negligible because number of turns is equal to 0. So this is all about the self-inductance of a solenoid. Now let us derive one more expression, that is energy stored in an inductor or in the coil, which is denoted by U. An expression for energy stored in an inductor or energy stored in the coil, and it is denoted by U, and this derivation carries 3 marks in your annual examination. So first we have to know what is inductor. Resistor, capacitor, likewise this is inductor. We know that a resistor opposes the current. Capacitor stores the charges. Likewise inductor it is a circuit element. What is inductor? Inductor is circuit element, and this circuit element opposes. What it opposes? This inductor opposes changing current flowing through it. Changing current flowing through it, it will oppose. What it mean? We know that resistor opposes current, electric current, but inductor opposes changing current. For example, when we considered AC or alternating current, the current is continuously changing, so it is opposed by inductor. Yes, what is inductor? Inductor is a circuit element which opposes changing current flowing through it, because We know that when the current changes, magnetic field also changes. When magnetic field changes, one more current is produced and that current opposes changing current in the same coil. Is it clear? Yes, what is inductor? Inductor is a circuit element which opposes changing current flowing through it. Now let us derive energy stored in an inductor. Here I am going to consider the work done in developing the current I. If you want to develop or generate electric current in the coil, we have to do certain work. Let us take it as dW. What is dW? dW is work done in developing current. Work done in developing current in a time dt. Work done in developing the current in time dt in the inductor. Where we have to generate current? In the inductor. Then I am going to consider E. What is E here? E is the induced EMF in the inductor. Induced EMF in the inductor. Now I am going to write the equation. Observe here. The rate of doing work is given by the rate of doing work. The rate of doing work means I am going to write the equation dW equal to E into I. So what is this E into I? Observe here. We know that work done is given by the equation V into Q, or we know that potential difference, work done in bringing a unit positive charge, W equal to V into Q. W equal to V is potential difference, but here instead of potential difference we can consider E induced EMF into Q. So we want dW with respect to time, dW by dt, that gives E into dQ divided by dt. dQ by dt means this is the small amount of current. Small amount of work is done. So we can write dW equal to E into I. This is dW divided by dt equal to E into I, or we can write dW equal to E into I into dt. We can take to RHS side. So let us take it as equation number 1. dW equal to E I dt. This is equation 1. We know that self-inductance is generally given by the equation E equal to L into di divided by dt. So about this equation we studied in the previous class. Let us take it as equation 2. Now substitute equation 2 in equation 1. What we can get? Observe here. Substitute equation 2 in equation 1. Equation 2 is E equal to L di by dt. That we have to substitute in equation 1. Equation 1 is dW equal to E I dt. Here I am going to substitute the value of E here. dW equal to I, keep as it is. In place of E, L into di divided by dt into dt. Or we can write this equation as L into I into di, because dt will get cancelled. Let us take it as equation number 3. This is the small work done to generate or to develop the current in the inductor. dW equal to Li di. Now I want total work done. To get total work done means we have to integrate equation 3. Integrating equation number 3. Integrating equation 3. To get total work done, W is equal to integrating dW from 0 to total current I. Substitute the values here. W equal to integration of from the limit 0 to I. dW means what here? L into I into di. Now let us solve this equation to get the total work done. Here I am going to write W equal to L is a self-inductance or coefficient of self-induction, and this is a constant. We cannot integrate. Let us take outside. Remaining is I into di from the limit 0 to I. Or this equation can be written as L into Integration of I into di, that gives I square divided by 2 from the limit 0 to I. Integration of x raised to n, that is x raised to n plus 1 divided by n plus 1, that formula we can use here. Or I am going to write W equal to L into, apply the limits, upper limit minus lower limit, I square by 2 minus 0, upper limit minus lower limit. Or we can write L into I square divided by 2, or we can write W equal to 1 by 2, take outside, L I square. W equal to half Li square. This is the energy stored in an inductor. So total work done means it is equal to energy. So U equal to, I am going to write half Li square. U equal to 1 by 2 Li square. This is the expression for energy stored in the inductor. So this work done is stored as magnetic potential energy in the inductor. The work done, whatever the work is done to develop the current, this work done is stored as magnetic potential energy in the inductor. Is it clear? So this is all about energy stored in an inductor.